I'm Colin Walls, and I'm here again to talk about embedded software. Now today what I want to talk about is the use of floating point in embedded applications. Now floating point is used when you want to do calculations which need a wider range of values essentially than integers will provide, and also other kinds of arithmetic operations like trigonometry and so forth tend to need floating point. Now the way floating point is implemented is typically using a standard format, that'll be IEEE 754 is the standard, which stores the floating point number as two integers. One is the mantissa and the other is the exponent. So the exponent is a power of 2 which is multiplied by the mantissa. So that's how the number is represented, and it gives you a very wide range whether you use 32 or 64-bit variants of that. Nothing comes for free. There's a cost of using floating point, and that cost is performance. It takes longer to do floating point calculations than it does to do integers. But there is also some issues around precision, because floating point numbers give you a wide range, but they're not necessarily absolutely precise. An integer has a value and it's easily determined. So the number 3 is the number 3. With floating point, life isn't quite that simple. So for example, if you write code like this, we have a variable x, which is of type float, and we are executing some code conditionally depending on the value of x being 3. Well, actually, the value of x isn't 3, it's 3.0. However, it's quite unlikely that x will ever be exactly 3.0. It might be 2.9999999 or 3.000000001, so effectively 3.0, but not actually 3.0. So therefore, it could have that value, but actually this if will still fail. That's typical of the kind of problems you can have with floating point if you're not careful. So equality is a no-no. This is also a possibility when you do greater than and less than. So if you write a for loop like this, where we're going from values of x from 0.0 up to 5.0, where we don't actually want the value 5.0 to be used, so effectively we are saying 0, 1, 2, 3 and 4. Standard for loop notation. However, the test of x being less than 5.0 will still be true if x is actually 4.99999. In other words, more or less 5.0, but not quite there, and that is entirely possible. So what you get is one more turn round the loop than you actually want. So a good rule here is do not use floating point numbers to control for loops or their like. You can write a for loop like this instead. It's very straightforward. We just introduce another variable, in this case I, which is an integer. We use that to control the for loop, but our variable x is still there and it is incremented in the for loop in the same way. It just isn't tested to measure the end of the for loop. That's a little taste of how floating point works and its impact. If you follow various programming standards, you'll find that your application of floating point will be limited by those programming standards to avoid some of these problems, and some others beside. But I hope that gives you some idea of what floating point's all about. And I'll be back again sometime soon with other things to say about embedded software. So until then, bye for now.